Hello everyone and welcome to this lecture where we are going to start with the example of our Corbel system. So this is the example that we are going to follow in order to analyze and design our Corbel system. So we can see here that we have a VU of 150 kilonewtons, and we are going to see how are we supposed to calculate NUC when it's not given. Our dimensions are 200 by 400. Our concrete strength F prime C is 25. Our steel grade is 400. Our concrete cover is 50 millimeters. So this is my Fy, which is 400. Now, to find NUC, we said that NUC is there due to two conditions. My first condition is that my beam is restricted from this area. My beam is undergoing bending, and due to this action, my beam is applying a lateral force that is tension force, and I should reinforce my corbel in order to resist this tension force. Now the second condition is due to temperature. I have NUC also due to temperature effects. Now trying to calculate NUC due to temperature effects is going to be very hard and very complicated. So what we do is we take a practical assumption into consideration, which is that my NUC equals 0.2 VU, which means that my NUC equals 0.2 times 150, which is equals to 30 kilonewtons. So this is how we basically find our NUC. Now when it comes to my compression, we're going to have compression here. However, this compression is going to be applied along this area, and this concrete area is big enough to resist the compression that is being applied on it. So we don't really have to reinforce against compression. We only have to reinforce against tension. So now we said we are going to distribute our shear reinforcement along this direction. However, what is the depth at which we are going to distribute these shear reinforcement? Now, of course, we are not going to distribute them along the whole edge here. There's a certain depth that we need to distribute them along. So what is this depth? What is this value of this depth? So let's take a look at this image to get a better look at the value of the depth. So here this is basically the detailing of our reinforcement. We can see the reinforcements that are required along with the values, but what we care about here is this value here, which says that the depth at which I am going to distribute my shear reinforcement is going to be 2 over 3D, my D being 400. So this means that my depth for shear reinforcement is going to be 2 over 3 times 400, which is equals to 270 centimeters, or millimeters, I'm sorry. Now we are going to round this up to 300 millimeters. So this is basically the depth at which I am going to distribute my shear reinforcement. So now we basically have everything that is required. We know our NUC, the depth where I'm going to distribute my shear reinforcement, my F prime C, my Fy, VU, and my cover. So we can go to our software, which is RCM ACI Builder. Now this software is very simple and easy to use, and it can be used to design special elements such as corbels and beam ledges. However, we can also use it to design beams, slabs, footings, and pile caps, and you can see the different types of beam slabs or footings and pile caps that are available within this software. It's a very sophisticated software that can be used, and it's very convenient to use. So let's select Corbel and brackets. First question is F prime C. Our F prime C is 25. Said our Fy is 400. Now the corbel height. Now my corbel height is, or should be, enough to resist the bending moment that is being applied on my corbel, and we said before that my corbel is represented as a cantilever, a short cantilever. So the bending moment is going to be max at the fixity, and it's going to reach 0 where my VU is applied, and it's going to remain 0 along the remaining length. So this is basically the bending moment diagram, and the H for this Corbel should be enough to resist this bending. So we have an H of 400, we have a B of 200, the cover is 50. Now the bearing loaded area LP and WP. So what the software is asking from us here is basically it is asking about the dimensions of my steel plate. Now when we talk about my steel plate, we said my steel plate is what's going to transfer my VU from my steel plate to my corbel, and then my corbel is going to transfer it to my columns. Now we need to make sure, like when we are talking about the bearing loaded area, we need to take into consideration the bearing capacity or the bearing stresses. And we need to look at the code to see the limitations that this code set for me in terms of my bearing stresses. And the code says that P over A should be less than or equal to 0.2 F prime C. This is the limitation for my bearing stress. Now we are talking about our bearing loaded area. We need to make sure that my area, so when we are talking basically about my bearing stress as well, we need to make sure that the area that I have is enough and is good enough to transfer this shear from my steel plate to my corbel. So let's go back here. So we said P over A is less than or equal to 0.2 F prime C. My F prime C is 25, so P over A is less than or equal to 0.2 times 25, which is equal to 5 MPa. Implies A is greater than or equal to P over 5. So this A that we are finding here is my A minimum. The minimum A that we can use in order to have a good enough area to resist or to be able to transfer this shear stress. Now the P here is P service. However, what we have is we have the ultimate. We do not have the service dead load, and we do not have the service live load. So what we are going to do is we are going to take the average of 1.2 plus 1.6. So 1.2, it's 1.2 dead load plus 1.6 live load. We are going to take the average. So we are going to take 1.4, and we are going to do here plus A is greater than or equal to 150 times 10 to the power of 3 over 1.4 over 5 implies A equals, or A is greater than or equal, let's check the calculation, it's equal to 21428 millimeters squared. Now again, we said this is the minimum area that we require. Now let's take into consideration that we have a square section. So let's say B squared equals 21428 plus B equals radical 21428 implies B equals around 147 millimeters, or we can take it as 150. So this is basically my WP and my LP because we said they are equal. However, usually my LP is greater than my WP, and this is what we are going to do because here we found the minimum area that we need. So we can set our LP to be 200 millimeters and our WP to be 150 millimeters, and this way we are increasing the area, thus we are decreasing my bearing capacity, which means that we are doing something that is good. So This is what we are going to do, because if we follow this section here, you can see our LP is greater than our WP, and we are going to follow this. We're going to set this as 200 and this as 150. Now, the software is asking me for E1 and E2. Now we can see here, this is my E1 and this is my E2. So the distance from my column, let's say, to the beginning of my steel plate is E1. Now we have the distance of my steel plate, which is 150, which is my width of my steel plate, and we require E2, which is the distance from the steel plate and until the end of my corbel. So first of all, we need to find the length of my corbel, and usually we take the length of my corbel to be equals to h, so L equals h, so it equals 400. So let's just draw it here. So let's just draw this image. This is this is 150, and we have an A. From our image here, if we look at this image, we see that we have an A from here to the midpoint of my steel plate. My A is 100, so here this is 100 millimeters. This is E1 and this is E2, and the whole length, we said L equals H equals 400 millimeters. These are all millimeters. So E1 equals 150, or 100, the distance from here to half my steel plate, minus steel plate divided by 2. So it's basically minus half the distance of my steel plate. So it's equal to 100 minus 150 over 2, which is equal to 25 millimeters. Now my E2 equals, this is my E2, it's basically 400 minus 150 minus E1. So it's 400 minus 150, which is 250 minus E1. So it's equals to 400 minus 150 minus 25 equals 400 minus 150 is 250 minus 25 is 225 millimeters. So here we go back and we set our E1 as 25 and 225. Okay. Now we have our shear force due to dead load and due to live load. We said that we do not have our dead load and our live load. So what we can do in order to find them is we can assume our dead load and find a live load in order to have a VU of 150. So basically what we are going to do, so 1.2 VD plus 1.6 VL should be equal to 150. Now let's assume 1.2, let's assume VD to be 50 plus 1.6 VL equal 150. So this way my VL is going to be 56. So I assumed my VD and I found my VL in order for the total 1.2 times VD plus 1.6 times VL to be 150. So this is 50 and this is 56 kilonewtons. My horizontal tension force, which is basically my TU or my NUC, we said it is 30 as it is 0.2 times 150. Now my tensile steel bar diameter, it's basically this diameter that we are going to use. Let's start with a diameter of 16 millimeters. Now the number of stirrups or rows that are there. So basically it's asking us for how many rows of stirrups are we going to have. Let's keep it as 4, and the number of stirrup legs per row. So it's asking us about the legs that I'm going to have. So my stirrup from the inside, how many legs I'm going to have. So basically we're looking here at the side view. If you look at the plan view, if you have 2 legs, we're going to have something like this. It's going to look like this. If we have 4 legs, it's going to look something like this. 1, 2, 3, 4. So basically our software is asking us for the number of legs. We are going to keep it as 4 legs as well, and we can press calculate. Now Corbel shear span to depth ratio A over D equals 0.357 less than 1. Okay, so what my software is calculating here, it's basically calculating to see if my corbel is a short cantilever or a long cantilever. So basically the criteria that the software has set is that if this ratio is less than 1, then we have a corbel. We can consider it as a corbel. If it's usually greater than 2, then we consider it as a long cantilever, or basically as if we were working with a slab cantilever. Now if we move to my corbel reinforcement, my primary tension reinforcement ASC is 397.46 millimeters squared, provides steel 2 Tor 16. So this reinforcement is my main reinforcement basically. Now we need 2 Tor 16, so let's just reduce it to 14. Okay, so let's reduce it to 12. Let's try going for 4. Now these 4 bars, where are they being distributed? So let's just check it here. These 4 bars are being distributed along this distance 200 millimeters. 1, 2, 3, 4. So we need to make sure that this spacing that I have here is adequate for my concrete to smoothly pass through this spacing and for it to not segregate. So to do that, we need to find the spacing, and my spacing is basically 200 minus the cover, which is 2 times 25, so 50, over the number of spacings that I have, 1, 2, and 3. So 3, which is going to give me a value of 150 over 3, which is 50 millimeters. Now 50 millimeters or 5 centimeters is an adequate number. It's good, it's not bad. However, for safety factors, or stay more on the safe side, we are going to go for a value of, we are going to stick with 3 bars better than going with 4 bars. So we're going to stay with diameter of 14. Now the shear reinforcement that I have, AH, equals 118.73 millimeters squared, provides steel closed stirrups, 4 rows, each contains 4 legs of Tor 8. So here I have Tor 8 bars. So if we go back to this image here, okay, so here our steel reinforcement, our shear reinforcement is going to be Tor 8, 4 bars with 4 legs. Okay. These shear reinforcement are going to be distributed along 2 over 3D, whereas my main reinforcement is going to be distributed along this direction here. Now pay attention to one thing. If you go back here, we can see that this is my main reinforcement. So this is the reinforcement that is being used to resist tension. However, here, this reinforcement, I do not really need this reinforcement, but why am I placing it? So this reinforcement is being placed basically to connect, or as a connector for my shear stirrups. As my shear stirrups is connecting to this reinforcement bar here, and is connecting to this reinforcement. So it's handling, or it's keeping, or it's working as a connector or a connection for my shear stirrups for them to be placed. So for them to be placed correctly. So this is why this is the main functionality of this reinforcement. It's not here to resist anything. It's here to try and support, if you want to say, our uh, shear stirrups. So this is why we need to focus. This is why the pink color here, this reinforcement is in pink, whereas this reinforcement here is not colored the same as this one, because this is not my primary reinforcement that is there to resist tension. So its main function again is to just support my stirrups in order for my stirrups to have a connection from this side and from this side. So this is basically it for our first example, which is our Corbel. We were able to design, analyze and design our Corbel system in a very fast pace because of how easy RCM ACI Builder is to use. Now in our next lecture we are going to start with our beam ledge example, so I'll see you then.